All right, here's a brief video talking about decimals, a little bit of conversions between fractions and decimals, and mentioning tolerance as well. Perhaps you remember a place value chart from back in the day, and of note here is where we have the decimal point. So if we're talking about a whole number, it gets built to the left of the decimal point. So if I had 871, there it is. We have 870 and 1, and we could think of this as 800 plus 70 plus 1. If I want to build decimals, first of all, observe we don't have a 1th. We start at the 10th right away, and the place value of that is 1 decimal place. And then as we go further and further to the right, we keep adding, counting up tenths, hundredths, thousandths, and the difference between that and our whole numbers is the th. Okay, and they don't quite line up what you expect them to be. Like hundredths only has 2 decimal places. You might think it would have 3 because 100 has 3, but think of the number of zeros in 100. There's 2 zeros in 100, 2 decimal places for hundredths. So if we were to make something of this, maybe we had 0.234, very complicated, and that means we have 2 tenths. So we're really just adding in to our number 2 tenths plus 3 hundredths plus 4 thousandths. Often when you're working, you're not going to have someone write something down. They're going to speak to you and they might say a decimal measurement in words, and you have to be able to understand what that is. It's easiest if someone says 12.72 volts on a battery, but it's also completely fair game for them to say 12 and 72 hundredths. So just really needing to know what that sounds like and what it looks like. So you're either going to see point or and for the decimal place, and then maybe you'll have 72 hundredths, or someone will just say 0.72. So as we look at these various examples, how would you say these? I'm probably going to use the and because it's a weirder one. For number 1, or A rather, it'd be 1 and 312 thousandths. Likewise, because we're still in the thousandths place value, B is going to be 1 and 12 thousandths. And same with C. C is going to be 1 and 2 thousandths. D, a little bit easier, it's going to be some big number, 23,415 and 4 tenths, because we're only going to that. Now, be careful. 4 tenths tells me that I'm only really accurate to this point. I haven't measured anything over here, but the minute I say 23,415 and 40 hundredths, it means I've been more accurate. So although they kind of are the same value, this number is more accurate. So in the previous example, that was you looking at something on a piece of paper and saying it to someone. Now, in this one, changing words to decimal, someone is telling you something and you have to write it down or interpret it. So if we had someone say a maximum clearance of 6 thousandths, well, we know we only have 6 of them, but they have to be in the thousands, so it's not right by the decimal. We have to put in those 2 zeros and the decimal point, and to be polite, always a 0 in front to recognize that that is 6 thousandths instead of hundredths or tenths. For B, a measurement of 176. Okay, I can commit to 176, and means a decimal place, and 35 hundredths millimeters. Oh, that's terrible. Anyway, 35 hundredths end in the second decimal place. So there we go. And for C, 2,000 and 500 10 thousandths. So, oh, careful, the and is confusing there. So 2,000 is our whole number. Our decimal place is for the and we have 510,000. So let's even think. We have tenths, hundredths, thousandths, 10,000. So we need to end the number here, and the number is 500. So this is a very confusing, very accurate measurement. There you go. So it's a measurement that's accurate to 4 decimal places. And as always, rounding is huge in decimals. Everyone hates it, but it's still the same. So let's look at this question. And this is kind of the same as whole number rounding. There's no difference, but for some reason people like it even less when it's in the right of the decimal place. Okay. So if we have this number 11 point, and I'm just going to read it out, 7632. And we want to round it to the nearest tenth. So I can ask you two ways. I can say to the one decimal place, but it's also totally valid for me to say to the nearest tenth of a liter, because that is the same thing and you should know that. So just like before, we're going to think about how many digits the answer will have. Well, the 11 is going to be there and our last digit will be in the tenth place. Okay, now that can either stay a 7 or go up to an 8. Those are my two options. It can change up 1 or stay. You look to the number that you're going to get rid of and only to the number to the immediate right. So the 6 describes what's going to happen. If you have a 6, that's higher than 5 or higher. So you're going to round up. So the 6 is going to knock the 7 up to this 8 and then disappear. And that is always the rule for us, unless it's something when we're doing, and I specify and we talk about it and we're doing ordering or something, or, people where we round up or round down in the same way every time. If it's general rounding, I want you to round up if you have 5 or higher, and I want you to stay there if you have 4 or below. So for all of these practice questions, I'm just going to kind of start with A, B, and C looking, I'm going to the nearest tenth. So I'm just going to highlight how long my number will be. In each case, it's going to only have one decimal place. And let's see what it's going to look like. So looking at A, 2.1 and then 3 decides what happens. 3 is below the number 5, so we're going to drop everything and the 1 stays. It does not change to a 2. In the second one, I have 3.0 and a 5 decides the behavior. 5 means round up, so 0 changes to a 1. In our next one, I have 4.9 and then 7 describes a behavior. So if you have 0.97, it wants to round up. So that 9 wants to round up, but there's no digit. So we're going to roll that over to a 0, but the effect that's going to have is to roll the 4 to a 5. So 4.97 rounds up to 5.0. And if that's confusing, just think about when you go shopping and everything's always listed for like $4.99. You know in your head that's essentially $5. It rolls over. Okay, looking at the same numbers, but this time we're going to round to the nearest thousandth. So I'm going to go tenth, hundredth, thousand. So I'm going to have 3 decimal places in each of my answers. And going again, the 9 forces this 9 up to a 0, which in turn is going to force a 3 to a 4. So just like you're looking at 39 turns into 40. And when you write that, you do 2.14 and you keep the 0 because we're rounding to the third decimal place. So we don't just drop it because then it would be rounded to the second decimal place, and that doesn't imply the same thing necessarily. Looking at E, the 2 describes the behavior of the other 2, and we get 3.052 because it stays. And looking at F, the 5 is going to tell us what the 8 to the left of it does. It's going to go up, so we're going to have 4.979. And lastly, we round to the nearest hundredth, which is the second decimal place. There we go. And for G, we're going to get the same kind of thing happening there. It's still a 9, but it's going to roll it up only to 2.14 because we don't have that double 9 anymore. And for H, the 2 means stay, 3.05. And for I, the 8 says the 7 goes up, 4.98. There we go. Okay, we've learned about three kind of fractions. We have proper fractions where the number on the top is smaller than the number on the bottom, numerator is smaller than denominator. Improper, where the numerator is bigger than the denominator, and that could be also expressed as a mixed number where we have a whole number in a proper fraction. When you want to convert fractions to decimals, the math is pretty easy. For proper and improper, you're just going to do numerator divided by denominator, top divided by bottom. The same way we're checking to see if fractions are equivalent. So here all we have to do is 7 divided by 8, and that gives us 0.875. So that is the decimal equivalent of 7/8. For a second, 3 divided by 16 gives me 0.1875, and these are all starting with 0 because they are not fractions greater than 1, so I expect to see 0 point something. If I move to improper fractions, you can still do numerator divided by denominator, but because I know these fractions are bigger than 1, the numerator is bigger than the denominator, I'm fully expecting to have, 3 point something, 4 point something, 2 point something. That means I'm doing it right. So here, 17 divided by 8, which gives me 2.125. Perfect. 83 divided by 16 gives me 5.1875. There we go. The only weird thing happens with mixed numbers, and all you have to do there is only deal with the fraction and bring the whole number along for the ride. You're going to keep the 2, and then you put a decimal place, and then you put whatever 1 divided by 8 is. So in this case, 1 divided by 8 is 0.125. Therefore, I just kind of add that to the 2 that I already have and get 2.125. Likewise, for 34 and 15/16, I know it's going to be 34 point whatever 15 divided by 16 is, and that happens to be 0.9375. So like I'm adding them together. This is an important slide. We're going to talk about making decimals into fractions. And in our trades, sometimes we want to have an exact value, right? We want our decimal to be 0.84 for this 14.84, but we want our fraction to also to have exactly the same value, 0.84. And sometimes we want to just kind of get close, like we want to think of it as a fraction over 4 or 8 or 16 or 32, those common imperial measurement fractions we see. So let's look at the traditional how to get an exact fraction. So if I had 14.84, the 14 is going to come along no matter what. The starting point for you is to count how many decimal places you have. Here we have 2, and that's the number of zeros that you get on the bottom. And your bottom fraction will always be a power of 10 to start. So I put a 1 in front, and the 8 and the 4 match 2 zeros. That makes sense because look, it's 2 decimal places. It's hundredths, and here is a hundredth. So we start here. And then you always owe it to me to reduce this fraction as much as you can. 84 and 100 are both divisible by 4, so we can reduce this to 21 over 25. And if I were to check and take 21 divided by 25, I would get 0.84. So these are exactly the same value. Now, on my measuring tape, I don't have 25ths. I have quarters, eighths, sixteenths, and so on. So these are values we often like to have. And the really neat thing about changing a decimal to a fraction is you can make an estimate. You can force any fraction to happen. So if I want to make quarters, that means I want to make something over 4. So my action will be, and I'm always going to bring that 14 along for the ride, but I'm going to take that 0.84 and I'm going to multiply it by the denominator I want. I want to make a denominator of 4. So I do 0.84 over 4, times 4, which gives me 3.36. So right now, I have 14 and 3.36 over 4. That's exact. But we don't ever mix decimals and fractions. So we're going to change that into 14, and we round to the nearest at this point, and 3/4. So how close are we to 14.84? Well, if you divide 3 over 4, we're at 14.75. So we're not exact, but we're fairly close. How do we get closer? Smaller divisions. To make eighths, fractions over 8, we have our 14, and we're going to do the decimal portion, 0.84, and we're going to multiply by what we want to make. We want denominators that are eighths. When we do that math, we get 6.72. So the exact value of this fraction is 14 and 6.72 over 8. Once again, we don't like to mix a decimal on top of a fraction, so we round the numerator to the closest whole number, and we're going to express that as 14 and 7/8, which, if I go the other way, divide 7 by 8, is going to be 14.875. Not quite 84, but closer. If I want an even better estimate, or my tape measure goes to 16ths, or whatever have you, 14 and 0.84 times 16. That's going to give me 13.44. Here we go again. We have 14 and 13.44 over 16, which is closest to 14 and 13/16. And once again, if we divide 13 by 16 just to see how close we are to 14.84, we're going to get 14.8125. So getting closer and closer, but never quite exact like 14 and 21 over 25 was. But a cool trick. And just taking the same concept and putting in a couple of little word problems. So say I need to drill a hole and I measure it to be 0.144 inches, or 114 thousandths of an inch in diameter. What is the bit size I should use? And I want to have a set that has, drill bits to the nearest 32nd. So I'm going to take that decimal measure and I'm going to turn it into a fraction over 32 by multiplying by the denominator I want. When I do that math, I'm going to get 3.648. So what I'm telling myself is, 3.648 over 32 is the bit size I should use. That's closer to 4 30-seconds. I look through my things and I don't have any 4 30-seconds. Why not? Because that's the same as 2/16, reducing your fraction. And I don't see any 2/16 drill bits either, because 2/16 is the same as 1/8. So even though they asked to the nearest 32nd, the nearest 32nd was 4 30-seconds, which could be reduced to 1/8. Now, is the 1/8 drill bit going to be bigger and smaller than the hole I want? Well, the 0.114 was only 3.648 30-seconds. And I'm picking something, the closest thing is 4 30-seconds. So my hole that I drill with a 1/8 drill bit will be a little bit bigger than the hole I was aiming for. Same thing for the second. We have a hole number 23. That's going to be part of our inch measurements. So remembering those 2 ticks are inches. 23 and the nearest 16th of an inch. So I take the decimal part, 0.658, and I multiply by 16. And that gives me 10.258. So I'm sitting at, I know, 23 and 10.258. Oh, sorry, 528. My bad. A little bit of number flipperoo there. Let's try that again. 10.528. 528 over 16, which is ridiculous. So we change that to 23 and 11 over 16 inches. Something we often see if we're working with metal and machinery and that kind of stuff are tolerances, an allowable range of size for something. This happens when you have wear, especially in automotive. You get out of round, you get wobble, you wear down your brake rotors, something like that. If we have a tolerance, sometimes it can be just, a plus or a minus. But if it's plus or minus, and that's what we call that, plus or minus, the plus on top of the minus sign, then your tolerance can go above or below the stated measurement. So if we have an accepted diameter of 4.25 plus or minus 0.02, that's giving me a range when I measure it. So it's saying this piston, when you measure it, has to be between a minimum size of 4.25 minus 2 thou, which is 4.248, and it can go all the way up to 4.25 plus 2 thou, which is 4.252. After that, if you're below or above that, you are out of spec. So here's an example of a tolerance. We have a cylinder bore, and brand new, it is going to be 4.255. Over time, the top part of your bore wears because that's where all the action happens when you're doing combustion and all that. So we expect it to get bigger here. So if we go out of spec, it's because the top of the cylinder will be bigger than the bottom. That's here nor there. Let's figure out what the acceptable range is. I see 4.255 plus or minus 0.0037 or 37/10,000ths of an inch. So that means if I take 4.255 plus 0.0037, my maximum allowable diameter would be 4.2587. And if I take 4.255 minus 0.0037, my minimum allowable diameter, which I don't know how that happened, gunk would build up, swelling would happen, who knows, 2513. So this is a range that is allowed to happen. And they're saying that they measured right here 4.2578. Is the cylinder still within specification? Well, it's allowed to go up to 4.2587. We're not there yet, so yes, it is.